Now, last time I left off with us talking about how we could simplify multiplying underneath the square root. So we could think of multiplying underneath the square root. We got square root of a times square root of b equals square root of a times b, and we could prove all that out. Now, this one here becomes a little bit more challenging. Can we think of a way where we can look at fourth root of a times the third root of b, and can we simplify this underneath one common radical? This one requires a little bit of creativity. And it also requires a slight change in perspective, which is why if I was going to explore this, I would first start off by rewriting this as a to the 1/4 times b to the 1/3. Why would I want to do that? Well, this is my way of trying to capture that I have a fourth root here and I have a third root here, and I can't combine them unless I had a common root. And maybe in your mind that's sparking in another phrase we have that has the word common in it, like a common denominator. Well, that's what makes me think that I might need to turn it into these first. So how could I continue working on this? A common denominator between fourth and third would be a 12th. And I could think of multiplying the top and bottom of this 1/4 by 3 to get 3 over 12. And I can multiply the top and bottom of this b by 4, so I get 4/12. And now notice what it is that I've been able to create, something that I could actually simplify a little bit more. I could look at this as saying I have an a to the third power, a b to the fourth power, and I could look at that all underneath a 12th root. And so the way that you can abstract this back and you can connect this, if it feels a little bit weird, is think about this as being one of 4 parts I need for my a to be completed. And I have one of 3 parts I need for my b to be completed in terms of multiplication. If I wanted to combine all of those into something that had common parts, then I might need to look for a common partition, a common multiplicative partition, like a 12th root that got everything back to its certain number of parts. And here again, we have nice parallels between parts and exponents and fractional exponents and radicals. It all plays together as just a slight change in perspective that allows us to look at questions like this much more easily. And if you don't believe me, here's the challenge that I have for you. We have the fourth root of a times the third root of b, and I claim that it's equal to the 12th root of a cubed times b to the 4th. And if you don't believe me, here's what I'm going to ask you to do. Multiply this out 12 times, and multiply this out 12 times. What you're going to see is that on the right-hand side, you're going to get a cubed and b to the 4th, no problem. On the left-hand side, you're going to get 12 of these fourth roots. And if you think of every 4 of them as taking care of the radical, as being enough to get us to a solid part, that would leave you with 3 groups of fourths. That gets you a cubed. And similarly with the b, you would have 12 of these cube root of b's running around, and for every 3 you would get a b that remains kind of untouched or back to its original state. And so for every 3 of these 12, that would leave you with 4 total. And here you have it. Whether you want to look at it in terms of fractional exponents, whether you want to look at it in terms of radicals, it all means the same thing. So let's now take a look down here at some of the things we can do with variables. So we're going to assume that these all are non-negative values, and that's important so that we make sure we're not accidentally doing a square root of a negative or an even root of a negative. But let's multiply this all through and see how our shortcuts can help us make quick work of some of these simple problems. I now know that if I multiply things through on the outside of radicals, that I can just keep those on the outside of radicals. And I know that I need to distribute here. So I'm going to do the first term. That's going to be 5 times 3 gets me 15. I've got the root 2x times root 2x gets me just 2x. So it's a square root of 2x and square root of 2x. That means the origins of an x square. And since I'm multiplying 2 of these origins together, I get back to my original square, my 2x. All right, and then I do it for the next term. That'd be 5. Well, I have the negative sign, 5 of these square roots of 2x times square root of 3, and I multiply that all underneath the square root. 2x times 3 gets me 6x. And so lo and behold, we have 30x minus 5 of these root 6x's. And that's all that we had to do. Let's take a look at the next problem. Assume that all the variables represent. How could we do a problem like this? Well, keep in mind, I like to look at this whenever we have it as a double distribution or we have parts being multiplied in terms of pictures. So we have 7 square roots of 2, and I have negative 2 square roots of 3. And let's imagine I'm multiplying that by a square root of 2 and a negative 5. I can represent that as a picture. I'll put it in a grid so I make sure that everything gets affected by everything else. So let's do it. 7 root 2s times a root 2, that's multiplying everything underneath the radical, so that'd be 7 root 4s. In other words, 7 times 2. So that's going to be 14. If that felt a little bit weird, take it a step back. I have 7 times the square root of 4, because I can multiply the 2 and the 2 underneath the radical. So it gets me 7 times 2 is 14. Let's keep going. Now on the other one, I have negative 2 times the square root of 6, because I can multiply the 2 and the 3 under the radical. Over here, I have two numbers on the outside of a radical. That'd be negative 35 root 2. I'd leave the root 2 alone. And then negative 5 times negative 2 gets me 10. And then I would leave everything underneath the radical alone. That'd be 3. The important part for problems like this is to not to get confused about what you're distributing to what. What we're really doing here is we've already set up our distribution grid, and now we're just multiplying everything on the outside by everything on the outside and everything on the inside by everything on the inside. And then we can combine it all at the end. I have 14, I have negative 2 root 6s, I have negative 35 root 2s, and I have 10 of these root 3s. So keep in mind, because this is multiplication, I'm multiplying this and this. I don't multiply the 5 and twice. That's not what distribution is. Distribution is when I'm affecting addition. And so I'm not distributing any more than I'm setting up my grid right here. And this would be my final answer. I couldn't simplify it anymore because root 6 is not something that can be factored. And then, or 6 is not something that can be factored. And 2 and 3 are both primes, so they can't be factored either. Now, if you'd like, instead of setting up this grid, you can move on to the Foil acronym. The Foil acronym is the exact same thing as the grid, but we just do it in parts. So we do it so that everything gets its individual turn. So we do the first terms, the outer terms, the inner terms, and the last terms. This is faster, but it requires you to pay a little bit of attention. So 7 root 2 times root 2 gets you 7 of these 2's, which gets you a total of 7. Well, if I guess I was going to do it fully, I'll do 7 root 2 times root 2. I'll do it all the way out at the first time. 7 root 2 times root 2, no problem. And then I do the outer terms. That'll be 7 root 2, negative 7 root 2 times 5. And then I have the inner terms. That would be negative 2. And then I have a root 3 being multiplied by a root 2. And then I have my last terms. That'd be a negative times a negative is a positive 2 root 3 times 5. So all in all, I could simplify this. I could say root 2 times root 2 is the same thing as root 2 squared, which cancels away to just give me 2. That's my 14. And then I have minus 35 of these root 2's. I have minus 2 of these root 6's. And I have 10 of these root 3's. And either way you do it, you will get the exact same answer. Very nice. Let's go into rationalizing denominators. Now, rationalizing denominators, what does that mean? Well, we know that rational, like rational numbers, doesn't mean the numbers that make sense. It means creating a ratio. So rationalizing a denominator means we need to create a ratio. And ratios, as we're familiar with, are normally between integer numbers, like 4 to 1 or 3 to 2. So if we talk about rationalizing a denominator, it just means turning a denominator into an integer. And why do we do it? Because it allows us to look at things more simply. If we talk about thirds and we talk about fourths, that works out well so long as that's the simplest way we can talk about it. We can find patterns, we can come to common ideas in our head. But if I have something like a square root of 2 on the denominator, like 1 over square root of 2, that's a little bit odd. I would like to look at that a little differently, and here's what I propose. If the square root of 2 is bothering me, I can't just square the bottom and square the top. That's not something that keeps the truth. Like that's not the same thing. I can't say that 1 over something squared is the same thing, because that would be that 1/4 is equal to 1/2. No, not true. Can't just square tops and bottoms. But I can multiply the top and bottom of a fraction by the same thing. So here's the strategy. Multiply it by its missing part, multiply it by its square root of 2, and multiply by the top to keep it balanced. Then on the top you'll get square root of 2, and on the bottom you'll get halves. Pretty fun. Now the reason why you would also want to do this is because, or at least why we used to do this, is because it made doing division actually quite a bit easier. Square root of 2 is a number. It's about 1.71, it's got some more decimals after that. But I want you to imagine that you are somebody trying to do some work without a calculator. Would it be easier to say I want to have the number 1 and I want to divide it by 1.71 ... Well, I could say how many times do I multiply 1.71 blah, blah, to go into 1? You'd have to kind of play around with exactly what that would be. It'd be maybe 0.7, 0.6, and you have to try it out and do it with all. That's a hard problem. Versus here, try this one. This one says that I have 1.71 ... and I'm dividing it by 2. Much easier calculations. I can say that if I want to multiply, how many times does 2 go into 1? It doesn't. How many times does 2 go into 17? It goes in there 8 times, and so I've got 8 times 2 gets me 16. I subtract, that gets me 1. I pull down a 1, and then I can go into my 5, and I can continue working on my number. So in olden times, when there weren't so many calculators, rationalizing a fraction allowed for the division to actually take place in a much easier way. Now, I'm hoping I got all of my numbers correct, that this actually is 1.71. Let's check it in our calculator, shall we? We're looking for what the square root of 2 actually would be. So I've got 2. I'm going to square root it. 1.41. So actually, let me correct this a little bit. I should have known that one because I use it all the time, but I didn't, and I make mistakes. So same idea, but if you want to correct your notes, we'll go through here and we'll say that this was actually 1.41. And so all of these would make it a little bit more difficult. And this number here would probably be, let's see, this would be a 7. 7 times 2 would give me 14. I would subtract that, I would get 0. I'd bring down the 1. I'd need to bring down the next number. And so I get some kind of number up here. And if we even wanted to check with our modern day calculators, if this is square root of 2 and I divide it by 2, sure enough, I get 0.707, which I was already along the lines of trying to get. 0.7, 0 would have fit in next, and then 7, etc. So, long story short, we're going to be rationalizing fractions because they allow us to identify things in a simpler way. Simpler being that if I needed to do them by hand, I could. If I needed to understand what they meant, I could, because now I'm talking about halves instead of fractions of square roots or square root fractions, however you want to think about that. And the most important thing in my mind is that the more that you bring things back down to a simplistic viewpoint of it, the more patterns you're going to recognize as you continue to study in math, as well as when you move into your field and you start looking for how math applies there. Square root of 2, I mentioned it before, is a very common number that you're going to see popping up for the next multiple semesters. And it's because it's actually one of the first irrational numbers that was discovered ever. And it happens all the time when you're dealing with triangles. And triangles happen much more often than you would think. Square root of 2 is literally the length of a triangle, a right triangle, that's made the simplest way. A side length of 1 and a side length of 1. This would be a square root of 2, that side length right there. And you can check that because you know the Pythagorean theorem by now. A squared plus b squared equals c squared gets you, in this case, 1 squared plus 1 squared is 2 equals c squared, so c has to be the square root of 2. All right, so we will be rationalizing the denominators. Let's see how we can use it to solve some more difficult problems like this. All right, so I have the square root of 7 divided by the square root of 5. Let's try to rationalize this. Remember, I cannot square root the top or square the top and the bottom. Don't get into the trap of trying to think that you can just do this. You're not allowed to just square things. It's not the same meaning. You're creating a whole new shape when you do that. And what we're trying to figure out is a different way of viewing the numbers I already have in front of me. So instead, let's do what I can do with fractions, which is multiply the bottom by something and multiply the top by the same thing. That just changes the perspective. So now I have square root of 7 times square root of 5. Well, multiplying inside of that radical gets me square root of 35, something I can't simplify, but on the denominator I get square root of 5 times square root of 5 is just 5. And here we are, we've rationalized our fraction. I've got it in terms of something I recognize, fifths. Let's do this next one. This would be square root of 3 over square root of 10x. And I can write it as doing a square root on the top and a square root on the bottom, because just like the rules we found out at the beginning of this lesson, I'm allowed to talk about taking square roots and affecting them to things that are being multiplied, or doing multiplication first and then square rooting. And since division is nothing more than multiplying by fractions, there's really no difference in thinking about what I could do first or what I could do second. So I can go ahead and take care of square root of 3 over square root of 10x. And to rationalize it, I need to multiply the top and bottom by the same thing, something that makes my denominator pretty. So let's go ahead and multiply it by the square root of 10x. That's going to get me, on the top, square root of 30x, and in the denominator I would have 10x. Very nice. I can't simplify 30 anymore. I could try. I'll factor it out. I get 3 and 10. That'd be 2 and 5. I have no pairs, so I can't pull anything out front of my radical. That's going to be as simple as we get. Now let's try this next one here. Now I've got the cubed root of 11 over the cubed root of 25x. Well, now I have one of 3 parts, and I really need the other 2 of my thirds here. So I'm going to multiply by the cubed root of 2x or 25x quantity squared. Why am I doing that? I'll show you in just a second if you're not seeing it already, but for right now, see if you can catch on, and then I'll explain it in a different way in a moment. So it's 25x quantity squared. So let's multiply that on through. What do I get? On the very top, I'm going to have 25 squared times 11. Ooh, what will that be? Let's pull that out. 25 times 25 times 11. Okay, that'll be 6,875. So I've got 6,875 x squared underneath a cubed root. And on the denominator, I have 25 x's squared and then multiplied once more gets me cubed, and a cubed root cancels away. So exactly what I would like. That gets me cubed root, I'll put it down here, cubed root of 6875x squared divided by 20, that should be in parentheses, excuse me, 25x. All right, can I simplify that at all? Let's see, 6875 factors into, well, I know how I got it in the first place. It was with 11 times 25 and times another 25. So that would be a 5 and a 5 and then a 5 and a 5. Okay, so I can find a group of 3 5s right there. I'll pull that out front. So that's going to equal 5 cubed root of whatever's left behind. 5 and 11 gives me 55. X squared over 25x. Oh, and I can simplify once more because I have a 5 on the top and a 25 on the bottom. That would give me a cubed root of 55 x squared over 5x. Whew, crazy. But that's exactly what happens when I try to rationalize the denominator. I'm trying to give it everything it needs so that I can eventually have 3 whole third parts or 2 whole square parts, whatever you really need. So, how to rationalize the denominator with 2 terms? The wrong way. Here's the warning for the wrong way. You do not want to be multiplying this by a square root of 3 plus 5. Now you might think that you would, because that's exactly what it seemed like we did before, but keep in mind before we had everything that was being square rooted. So we had a 1 part and we were just trying to create more and more parts. Here I've already got a whole. I've got this plus 3, or I've got this plus 5 here. Let me show you why you wouldn't want to square root 3 added to 5 and multiply that by the top and bottom. We'll just try it out. If I do that the first time, and I'll put it in this box, on the top I will have 2 square root of 3, and I will have 10. That's from distributing the 2 to the square root of 3 and 2 to the 10, no problem. On the denominator, I have this double distribution, this foiling that needs to happen. So I've got square root of 3 times square root of 3 is going to get me 3. I've got square root of 3 times 5 is going to get me 5 of these square roots of 3. And then I've got 5 times square root of 3 again gets me another 5 square root of 3. And then I've got 5 times 5 gets me 25. So all in all, after all of that work, all I've created is a big old mess for myself. I've got 2 square root of 3 plus 10 on the top, and on the denominator, I have 28 plus 10 root 3s. I've made no progress. I've still got that square root in the bottom. That's super frustrating. So I'll show you the trick. if you can take a moment and step back and say, where is it that we really fell into trouble here? Where is it that that pain really came from? It came from these two terms. These two terms are the things that have my square root of 3 in it still. If those weren't there, I wouldn't have a problem. Well, where did those come from? Those came from multiplying square root of 3 times this 5 and a square root of 3 times this 5. Well, let me show you what we could do instead if we're strategic about it, if we're careful. What if instead I had 2 and my square root of 3 plus 5 from the denominator, and instead of multiplying by the top and bottom by the exact denominator, I changed it just a bit, and I'll multiply it by square root of 3 minus 5 instead. I can still do that to the top and bottom, and it will maintain the exact same meaning. And now take a look at what's going to happen. 2 times the square root of 3 on the top is still going to get me 2 square root of 3, and then 2 times negative 5 is going to get me a negative 10. So I've got my square root at the top, that's fine, I don't really mind that. On the denominator, we're going to do our foiling, or our double distribution. Square root of 3 times square root of 3 gets me square root of 3 squared, which is just 3. Square root of 3 times negative 5 gets me a negative 5 square root of 3. 5 times 3 is going to get, or 5 times root 3 gets me a positive 5 root 3. And then 5 times negative 5 gets me a negative 25. And now, watch the magic. 2 root 3 minus 10 over these two terms cancel away and leave me with 3 minus 25 is negative 22. And that is a denominator that looks like a ratio. It's got 20 seconds on the bottom. That's perfect. So I want you to write yourself a little description here. Why is it that when we are doing all of this, we are multiplying by not just the exact denominator, but a modified denominator where we change the sign? What I'll give you some wording for is we say this is called multiplying by the conjugate. And I'll write that out for you. So conjugate. And the conjugate can be thought of as just simply if I have x plus y, then the conjugate gets me x minus y. So it's switching the sign of that second term. So we're multiplying by the conjugate, and that's going to be the words that I use as we're going through and practicing things. So write yourself, pause the video a moment here, write yourself why this works, and give yourself a reminder. Don't fall into the trap of trying to just square fractions. That changes the whole meaning and the whole shape. You're not allowed to do that. All you can do with fractions is do the same multiplication to the numerator as you do to the denominator. Okay. So now let's take a look down here at some of these other problems. Let's do for B. How can we really quickly rationalize by multiplying by the conjugate? So we've got 3 root x. The conjugate would be if I change the sign from negative to positive, and then I'll make sure I'll do that to the top as well. So 3 root x plus 4. Keep in mind that all I'm doing with fractions here is I'm multiplying by the top and bottom the exact same way that I would if I was trying to change it with normal numbers. So don't get confused about trying to get rid of these square roots and using any techniques other than what we're already allowed to do with fractions. All right, let's distribute this on through. 7 times this 3 root x is going to be 21 root x's, and then 7 times 4 will be 28. On the denominator, we're going to get 3 root x times 3 root x gets me 9, and then the root x times root x gets me just x, and then I'm going to add 12 root x's from my outer terms. My inner terms get me a negative 12 root x, and my last terms get me a negative 16. So all in all, my rationalizing comes to 21 root x plus 28 over, these two cancel away, and I have 9x minus 16. I see nothing common that I can divide the top and bottom by because I have not everything's even, not everything looks divisible by 3. I think we're just about done. So that's going to be my final answer. Not too bad. Let's do it quickly with this next one. Let's multiply the top and bottom by the conjugate. That would be square root of y minus 2, and we'll multiply the top by square root of y minus 2. Now I'm going to leave you with this one. All you're doing here is you're working on doing your foiling or your double distribution. Keep in mind that on the bottom, that's going to be where you multiply these two. And whenever you have two square roots that are being multiplied, and I do say square roots, they need to be square roots where 2 of them will allow it to cancel away. 2 square roots will cancel away the square root that is being squared will cancel away Square root times 2 is going to get you something. Square root times negative 2 is going to get you something. And then the 2 times the negative 2 gets you another term. Write all of those out on the denominator, 1, 2, 3, and 4. Then on the numerator, you've got the same idea. You got the first, the outer, the inner, and the last. Multiply all of those out and put those on the numerator. In between them should be plus and minus signs. And then see if there's a way you can simplify it any bit more. But you should always be able to check your work that you did it correctly, because these two terms will cancel away. So overall, we've looked at a couple of different things with radicals. The important thing with radicals is to keep in mind that radicals are just parts. You can think of them as fractions of multiplication. But it gets a little bit weird because we already have a definition for fractions in our head. So instead, think of them as parts. They're parts of a shape, parts of a square, parts of a cube. And when you get enough parts of them, you get the entire shape. So you no longer need to talk about that in terms of radicals. So now if you're either talking about them in cubes and you'd like to go backwards, you can use radicals. If you want to use radicals and find enough of them to make the shape, then the radicals go away. All of these come back to roots, and you can remove roots, radicals, exponents in the exact same way that you've been removing numbers in all of your algebra equations as far back as you've been studying algebra. So thanks for working through this. I know it can be a little bit challenging. Give yourself plenty of time to kind of soak and marinate in this material, and I'll see you for the next lesson.